Okay, let's just get right to the point here. At the end of the day, with this chemical equation of 2 moles of aluminum, 2 moles of sodium hydroxide, giving 3 moles of hydrogen, we were only able to produce a 49% yield at 34 liters of hydrogen. And delta T was 5 hours. It took 5 hours for this thing to finally stop bubbling where I gave up on it. And yet the next day it still produced a slight amount of gas, but it was such a slow trickle, I gave up. It was an unusable trickle. So delta T is, here we go, greater than 5 hours. You're going to see this again in the clip. I just want to get this up front so we know what's going on here with the hydrogen synthesizer. Okay fellas, so I got it opened up here. Try to get it directly into this light. I'm going to dump this out. We're going to see what's inside. Right here is the level line, and I want to show you something pretty interesting that math can show us with that information. Now, when you do a volume calculation on that space I just showed you, it turns out the volume is 0.44 liters. Now, if we take the graph information of the pressure change plot, the delta V, we see that 7 times we purged the tank. The first time we purged the tank, it was at 200 psi's, and so on. The third time it was at 250. So when you add all these up, you get a sum that physicists and engineers call the effective pressure. So what that tells us is, had we not cracked the valve during the entire chemical process or the reduction of sodium hydroxide, I'm not sure the actual name of that process. I think it's reduction. I don't think it's decomposition. Dissociation of hydrogen, I don't know. Anyway, with this information, we can tell using the effective pressure formula. You divide the effective pressure in psi by the current atmospheric pressure, and it tells you how many atmospheres are in that tank. And because we know how many atmospheres are in the tank, and because we know how many liters are in the tank, we multiply the two, and we get the sum of 34 liters of hydrogen gas being liberated in that reaction. Now, that comes out to 1.2 cubic feet of hydrogen gas at STP, which I believe to be 25 degrees Celsius, 14.5 psi atmospheric pressure. So that's kind of interesting. That's the actual yield of the gas. Now, I'm going to have to double check the math and see what the yield was. We were supposed to get 3 moles of hydrogen gas out of that reaction, okay? So, if we go 3 times 22.4, I need my calculator because I'm stupid. 3 times 22.4, that's 67.2 liters that the balanced equation said we were going to get. And I believe that was aluminum plus Na, 2 aluminum plus 2 NaOH equals 3 H2. Okay, that is what we did. We added 2 moles of aluminum, 2 moles of sodium hydroxide. I'm not sure how many moles of water that was. We used 400 milliliters of water, and 18 milliliters is a mole, so like a lot. We did not get no 67.2 liters, okay? So, matter of fact, 67 divided by 28, that would have come out to 2.4 cubic foot. And you know, the bag we seen did kind of look like it could have been 2 cubic foot, but I haven't actually built a box that's a cubic foot. It's bigger than you think when you look at it. I mean, I've built one on the job before, but not here, just to show you what it looks like. So gas laws are weird. They have like hyperbolic curves that they work under, meaning that at this pressure you're going to be here on the mathematics. At this pressure you're going to be here on the mathematics, and you can see that there's a discrepancy. So either we're seeing the discrepancy in the mathematics because I have not thoroughly reviewed these formulas. This has been a long time since I've used them, but this is a pretty cut and dry process. This is how these guys determine the tank size needed to run generators on propane and things like that. They use effective pressure. Same thing with oxygen and all that stuff. This is the formula they use. So, irregardless of the quantitative figures, the empirical data is showing that either I don't know what the hell I'm talking about, or it's common practice not to get 100% yield. We basically got about a 49% yield. And I've heard this term used in the production of chemicals and manufacturing. So if anybody who has a background in chemistry would elaborate on this or corroborate my assumption. Okay, fellas, I know what happened here. There's two things that took place. First of all, we have 19 grams of aluminum left over. Okay, so we got 19 grams of aluminum left over, and I know the reason why is because there's a secondary reaction that takes place between the sodium aluminate and the sodium hydroxide. And I'm not sure where those two equations are. Give me 1 second. Right here are the equations I was referring to, or the formulas, I'm sorry. You see that bottom formula? I believe if that takes place during the upper process, that it's using up sodium hydroxide to produce this right here, the Na6Al2O6. See how this reaction requires 6 moles of sodium hydroxide to get 3 moles of hydrogen, and I don't know what this XH2O is, but maybe that just means extra, a large quantity. So what's happening is this lower reaction is taking place, creating this substance below, and that's why we were unable to react all of the aluminum, is because some of it turned into this substance here. Control C, Control V. I don't know what it is. Okay, it isn't giving me much information regarding the actual name. Yeah, damn it. So, it's sodium aluminate or something like that. It doesn't really matter. Either way, that's what's happening. So, in order to react all of the hydrogen gas, we would have to add excessive amounts of sodium hydroxide. So there you have it. That's what you're going to get. I'm not going to go any further into this. I've got a lot more I could say. I could figure out exactly how much more sodium hydroxide, but I'm just not into it right now. This is just not going anywhere fast.